Alright, Electronics 2, we start at Chapter 6, BJT Amplifiers. The first section that we're going to discuss is Amplifier Operation, 6.1. Introduction, you basically had an introduction in Chapter 5 already. I want you to mark the introductory paragraph of 6.1. Basically sums up what you've done in Chapter 5 as well, where you had to do the different biasing circuits. Anyway, just to remind you again, what is biasing? Let's read there. The biasing of a transistor is purely a DC operation. The purpose of biasing is to establish a cue point about which variations in current and voltage can occur in response to an AC input signal. In applications where small signal voltages must be amplified, such as from an antenna or a microphone, variations about the cue point are relatively small. Amplifiers designed to handle these small AC signals are often referred to as small signal amplifiers. Alright, this is what we're going to discuss in this chapter as well. We're going to discuss various types of amplifiers, and even one of the amplifiers, the most common amplifier, which we will also start to discuss today, you will build in the lab, you will do the design, you will build it in the lab, look at the input signal on the oscilloscope, output signal on the oscilloscope and so forth, so that you understand the complete operation of this amplifier. Alright, but before we get there, still on page 257, just to make sure that we understand the names that are used for the quantities in this book. AC quantities, you are familiar with the DC quantities. If you can recall from previous chapters, DC quantities like VCE, we can see that the subscripts are capital letters. That of course refers to a DC quantity. If we look at these AC quantities like VCE peak to peak, for instance, I can see that the subscripts are lowercase to indicate that these are AC voltages. Alright, so familiarize yourself again here, what are RMS, average values and so forth, which will be also used in the semester as well. If you refer back to the textbook, you can mark there in the textbook, the first sentence there says DC quantities were identified by non-italic uppercase subscripts such as ICIE, as you can see there. Lowercase italic subscripts are used to indicate AC quantities of RMS peak and so forth, as indicated there. Instantaneous quantities are represented by both lowercase letters and subscripts, as you can see there, small I and small c and so forth. Just below the figure, we can also see, for example, RC is referring, RC with a lowercase c is referring to the AC resistance at the collector, and RC with a capital lowercase letter, of course, refers to the DC quantities. Alright, another thing that we're still going to discuss is the internal resistances of the transistor, which is named R accent. R accent are the most popular that we're going to use, but we will still discuss that as well. Alright, just to familiarize you with the quantities as being used in this textbook. Alright, just to refresh your memory again, you were introduced to a linear amplifier in Electronics 1 in Chapter 5. It's basically what you also looked at. If I look at the specific circuits, see that you have done biasing circuits in Chapter 5. What sort of biasing is used here? What type of biasing is used in the specific circuit? Voltage divider bias. Now, I can see that clearly because there's my supply, there's R1, R2 that is providing my voltage divider bias so that I can get a certain VB here, which will also, of course, cause me to give me my IBQ. Nah? Alright, once I've biased, I've seen that it is a DC operation, DC voltages. Once I've biased, then I can apply the signal that I want to amplify. There's my small signal that I'm amplifying, and I can see on the output I have an amplified signal, only it's 180 degrees out of phase, which we'll also discuss just now. Alright, so as I said, we will discuss this in full detail in the next following sections to come. Alright, also that, I will discuss that in full detail with you as well. But you are familiar with this. This comes from the transfer characteristic curve of a specific transistor where I've biased to determine a Q point there. Now that will be IBQ, gives me a Q point. I want my Q point to be approximately in the middle of the line, because I know for linear operation I want my amplifier to operate between the cutoff and saturation points. Now, otherwise I do get distortion. Alright, I just want to remind you again at this point how to use this book. Alright? As we are working through the sections, when you go home tonight or whenever, you have to go and work through the section, go and have a look at the examples, do the checkup questions, make sure that you understand the work that I discussed for that specific day. Né? And then if you go to the back of the chapter, you'll also find the basic problems related to these sections. Then you will go and try and do the basic problems related to this section. Eh? And on page 313 are the problems for this specific chapter. And I can see already there for section 6.1, where we discussed amplifier operation, there are already 2 questions. Né? So then you go and try the 2 questions. If you can't do it, you refer back to the section. Go and read again. Maybe there's something that you didn't understand. That is how the learning process takes place. Né? Then you try and figure out. If you still can't do it, the next time we get together, you ask me this question so that we can discuss it again. Make sure that you understand the work. Don't go and learn the work like a parrot. You have to understand it. Okay? It makes life much easier, and even one day you will be worth something as a technician or an engineer. Nah? By knowing something, not just learning it like a parrot. Anyway, let's carry on with section 6.2, transistor AC models. You can mark the introductory paragraph again. Always nice. The introductory paragraphs, it tells you more or less what this section is going to be about, what you're supposed to be learning, and so forth. Alright, to visualize the operation of a transistor in an amplifier circuit, it is often useful to represent the device by a model circuit. A transistor model circuit uses various internal transistor parameters to represent its operation. Transistor models are described in this section based on resistance or R parameters. Another system of parameters called H parameters is briefly described. So I will basically just give you an introduction to the H parameters. But let's have a look at the R parameters first. 5 R parameters commonly used for BJTs are given there in table 6.1. Now alpha and beta you are familiar with. You have done it under DC, but these are the AC quantities if you look at the lowercase subscripts. Né? Alright, so I can still see that alpha AC is still the ratio between collector current and emitter current. Beta AC is still just a ratio, no unit, between collector current and base current. The new ones that are introduced here, however, are the AC emitter resistance, the AC base resistance, the AC collector resistance. Indicated R and E, R accent B, R. Alright, in that section just following table 6.1, I also want to mark some stuff there. The R parameters transistor model as shown there in figure 6.5. I can simplify the R parameter model of the BJT. You can mark that sentence. It says there, the effect of the AC base resistance, R accent B, is usually small enough to neglect, so it can be replaced by a short. Right, so here I can see from the generalized R parameter, there's my R accent B, and if I look at the simplified, I can see that there's no resistance because it is so small that we can neglect it. Nah? So the simplified one. The next sentence you can also mark the AC collector resistance, R accent C, is usually several hundred kilo ohms and can be replaced by an open. And we can see it here as well. And in the simplified circuit, it's not there anymore, replaced by an open. Basically the same concept as we had when you had in electronics 1, where we discussed a diode. We've seen if the diode is reverse biased, it actually happens so with the electrons being moved away from the center. There's a very big resistance, so it acts as an open. Basically the same thing here, very high resistance, so we can regard it as an open. So the only one that's actually left is R accent E. And there's the simplified circuit there. Alright, so on page 261, there's a heading that says determining R accent E by a formula. And you have to know formula, or equation 6.1. That's a standard formula. The derivation is in Appendix B, but we're not going to look at the derivation of that. But R accent E is equivalent to 25 millivolts divided by IE. Please take note that IE is a, what is it, an AC or a DC quantity? DC quantity, very important. I'm calculating an AC quantity, but I'm using a DC quantity. So remember, underneath the DC analysis, you will calculate the value of IE, but I need that value to calculate the value of R accent E. So if I go and have a look at example 6.2, where they use this formula in an example, determine the R accent E of a transistor that is operating with a DC emitter current of 2 milliamps. So the 2 milliamps already been calculated. I just put 2 milliamps into this formula. I get a value in this specific case of 12.5 ohms, which brings me to the next point. Please note that the value of R accent E is quite small. It's normally between, I would say, 5 to 20 ohms. So if you calculate the value of R accent E and you get a value larger than that, you must know that you've made a mistake somewhere. So that's one way to check your answers, to know what type of answer you expect. Alright, that is determining R accent E then. Okay, so that concludes the R parameters. We see now that we only use the one. We're not going to use R accent B and R accent C, one being too small, the other one quite large. So I'm just calculating R accent E. Alright, the next thing I want to stop at is on the next page, where we have a look at the comparison between AC beta and DC beta. Alright, I can see here on the graph of IC against IB that the graph is non-linear. Non-linear. And you've also learned in Electronics 1 that beta DC is the ratio of IC over IB. But what do I know about DC? It's a constant value. It's set at the Q point there. So I have ICQ, I have IBQ, and I just calculate it in that way. But what do I know about DC? About AC? Sinusoidal signals we're going to use with the signal gen in the lab for our amplifiers is it changes all the time. Changes all the time. So what will I have around the Q point? With the signal now riding around my Q point that I want to amplify. Changes 50 times per second if I use a sinusoidal signal at 50 Hertz. So I will have a value that says delta IC. Changes all the time, and I will have delta IB. So how do I calculate? Beta IC is going to be the change in the collector current divided by the change in the base current. Alright, now because this is not a linear graph, this value is not going to be the same as beta DC. It will differ a bit. It will be close, but it will not be the same because it's not a linear graph. Now I want you to make a note at this point. With the calculations or the designs or whatever we're going to do this semester, if you have only the value of beta DC available, which I normally get from the data sheet, and I have to do AC calculations, I can use beta DC to do my AC calculations as well, because I don't have beta AC. And vice versa, if I only have beta AC and I have to do DC and AC calculations, then I use it for both. But in some cases I have beta DC and beta AC, then of course I will use DC with DC, AC with AC. Alright, so just make a note of that. Alright, so that's just a comparison between AC beta and DC beta. You've learned quite a few things about beta as well in the previous chapter. I hope you still remember. Beta, for instance, is it a constant value? If I may ask a question. Is beta a constant value? It's not a constant value. What influences the value of beta? If you can remember that graph, the graph was on the vertical axis, it was the value of beta, and on the horizontal axis, they had a value of some sort, and also there were various graphs at various values of what? What were those? Temperature, nah. Temperature influences, so you could see as temperature changes, the beta value also changes, but also if what else changes, what also influences the value of beta? IC, nah. As the current IC, collector current changes, it also influences beta, nah. So it's important. And why is the beta important? What have we learned in chapter 4 about beta? What is a transistor actually? What does it amplify? It's a current amplifier, nah. It's a current amplifier. IC is beta times IB, nah. Actually a current amplifier. So beta plays quite a large role in my amplifications, nah. But we will discuss more about that in the later sections. Alright, on page 262, I'm just going to do the introduction of the H parameters. You can underline that first sentence. The first sentence says a manufacturer's data sheet typically specifies H, or which is actually called hybrid parameters like HI, HR, HF, and HO, because they are relatively easy to measure. So the manufacturer used these values to do some measurements to give us some more information on the data sheet of a specific device, which we again then can go and use when we go and do a design of a specific circuit, being it an amplifier or whatever. Now, there are a lot of involved formulas to do calculations with H parameters, but we're not going to do it this semester. We're just going to use the R parameters. But I still have to introduce you to these parameters so that you at least know about them. It won't be examined. You just have to know about them. All right, in table 6.2, the H parameter names, as we've already seen. HI is the input impedance. It's a resistance. The condition under which it's measured is with the output shorted. HR is the voltage feedback ratio with the input open. HF is the forward current gain with the output shorted. And HO is the output admittance or conductance with the input open. All right, now in 6.3, you can see that these subscripts gets changed for the different configurations of amplifiers. Now in the next section I will explain to you how to differentiate between the different configurations of amplifiers. But you will see there's only 3. What is the clue? The transistor only has 3 terminals, nah. So you can see it relates to the terminals. If I go and look at the names, common emitter, common base, common collector. Those are the 3 configurations, but I will show you in the next section how to differentiate between these configurations. But now I can see that my H parameters names changes depending on the configuration of amplifier. HI is not only HI now. If I use a common emitter, it's HIE. If I use a common base, it's HIB, and so forth. Now, then I know these parameters refer to a specific configuration of amplifier. All right, lastly, there's the relationship of H parameters and R parameters. I think we're already familiar at least with beta HC, which in this case, it's the lowercase letters, nah, HFE, but you know the DC quantity, nah? Because you also found it on the data sheet. What is beta DC on a data sheet? It's also HFE, can you remember? But it was capital letters, nah? To show that it was a DC quantity. You won't find beta on a data sheet. It's called HFE on the data sheet. No, it's a hybrid parameter. All right, also alpha AC, HFB, and then on the next page you can see I can use the H parameters to determine the R parameters. But we're not going to do that. Just know that it is available if you do need it some stage in your career. All right, that you can use it. But of course we're going to determine R accent E by that standard formula of 25 millivolts divided by IE. So we stick with that one. Eh? All right, again, read through the section. Do the check-up questions. After you've done that, basic problems at the end of the chapter to check if you can do everything. If you can't, refer back to the section. Make sure that you understand the work. Now, you have to understand and then of course learn the basics. It makes life much easier to understand electronics, right? There are standard rules. It's like a recipe to bake a cake. Standard rules. If you know the rules, you won't have any problems understanding electronics. All right, this concludes this session then, 6.2.